Math 1314, Tyler Junior College, section 5.1, 2 by 2 linear systems of equations. Solving a 2 by 2 system by graphing. I think the caffeine in this drink I'm drinking is finally starting to kick in. So my apologies if I came across as a little lethargic in the first two videos. Speaking of the first two videos, we've learned the terminology for describing systems of equations, and we learned the straightforward technique for verifying if an ordered pair is a solution to a 2 by 2 system. In a nutshell, if it makes all the equations in the system true simultaneously, then an ordered pair is a solution to that system. But what we haven't talked about is how to get that solution in the first place. Off the top of my head, I know of at least a half dozen ways to solve a 2 by 2 system of equations. I won't be sharing all of them with you in this series of videos because some of them are a little beyond the scope of this course. But I will be sharing 3 techniques with you, starting with graphing. Recall that a graph is just a visual representation of the solutions to an equation. If an ordered pair makes an equation true, that point belongs to the graph, otherwise it doesn't. If you put enough solutions on a coordinate plane, you start seeing the graph emerge. So it stands to reason that if we are looking for a solution to a system of equations, we are looking for an ordered pair that would be on the graphs of all of the equations involved in the system. In the case of a 2 by 2 linear system, that means we're looking for the point where 2 lines intersect. Disclaimer, I would never do this by hand. I would only use technology for finding the solution to a system of equations by graphing. I'll explain why at the end. But for now, let's see if we can solve this system. Y equals 2x plus 3 and y equals negative x plus 6. You may recognize this system as the first system in the examples in the previous video. So you already know one solution to it if you saw that video. But let's pretend that didn't happen. If I want to find the solution to the system by graphing, I need to graph each one. Luckily, we've had plenty of experience graphing things in slope-intercept form. In the first equation, y equals 2x plus 3, we know the slope is 2 and we know the y-intercept is 3. We can use that information along with a very as accurate as I can draw it, accurately drawn x and y axis where each mark is the same distance. If you were to measure, each one is 2 inches. Let's use this coordinate plane to graph y equals 2x plus 3. The y-intercept is 3, so I can immediately go to the y-axis and put a point at 0, 3. And remember, to use the slope, think of it as a ratio of integers, in this case 2 over 1, and then interpret it in the context of a slope, rise over run. We would rise 2 and then run 1. If we rise 2 and run 1, that will put us right here, and I believe that point is 1, 5. Let's label these points. 0, 3, 1, 5. Get a straight edge, got one right here. Connect the dots. And if you wanted to, you could rise and run a second time to make sure that everything is the way it should be. Let me check something real quick. Should be crossing at negative 3 halves, which is about there. I was mentally calculating the x-intercept of this line to make sure that it's kind of in the right place. It's at negative 3 halves if you substitute 0 for the y and solve for x. All right, so there's our first line. Now let's graph the second one. For the second line, y equals negative x plus 6, that is also in slope-intercept form, so we can capitalize on that. We know the y-intercept is 6. 1, 2, 3, 4, 5, 6, so it's up here at 0, 6. I'm going to pull the slope out, m equals negative 1, because I want to look at it, first off, as the one that's invisible after the negative, and I want to look at it as a ratio, so that I can interpret it as rise over run. We will rise negative 1, meaning go down 1, and then run 1. If we start at the y-intercept, rise negative 1 and run 1, well, look at that. It'll put us at 1, 5 again. How coincidental? Not really. designed this problem that way. Okay. So now that we've got both linear equations sketched, the solution is represented by their intersection. But as we've already pointed out, that intersection is 1, 5. There's my black marker, here it is. Answer 1, 5. Now, can there be another solution? Well, that's like asking if these lines can intersect again, and they won't. And you might be thinking, wait a minute, in the previous example, we had a system and it did have 2 solutions. Remember, go back and watch the previous video. The second system, we checked 2 ordered pairs and they were both solutions. How could that be? Well, we'll discuss that in a later video in the series. But in general, to solve a system by graphing, you graph each line and you locate the intersection, the coordinates of the intersection of the solution. Now, why would I recommend never doing this by hand? Well, for a couple of reasons. Number one, accuracy is of the utmost importance. If I had just drawn these marks all willy-nilly, then they may not have intersected exactly where I think they would have. And secondly, who's to say that your solution is going to contain integers? It could contain fractions or decimals. For example, if the solution had been something like, I don't know, 11 fifths and 17 sixths, good luck identifying this ordered pair where 2 lines intersect. It is possible that the solutions to a 2x2, or the solution to a 2x2 linear system of equations could contain decimals or fractions, and therefore be difficult, if not impossible, to identify just by inspection. But if you have technology available to you, whether it's a website like Desmos.com or a common graphing utility like a TI Nspire or a TI 84 Plus, technologies like that can not only draw the graphs but give you the coordinates of the intersection point. Unfortunately, if those intersection points are fractions, it will give you decimals and sometimes they'll be rounded off. So even those technologies have a slight flaw unless your technology is sophisticated enough to give you the ordered pair as rational numbers, aka fractions. But in general, graphing is convenient because you get a visual of what you're looking for, but it's inconvenient in the sense that it better be drawn perfectly and you better hope that your solution is at an integer ordered pair. Otherwise, it'd be very difficult to locate that solution. So it's a nice approach in theory, but not very practical in reality. It does, but again, it does give you a visual of what the solution looks like. So if we're not going to solve these by graphing, how are we going to solve them? Well, I'll show you in the next video.